Well, good morning, all you people who can't get enough of transformers. I'm Leon White with H2 Scan, here to talk about the value of measuring hydrogen in transformers. I've spent pretty much all my career working with utilities, and about half my career working at a utility, and the other half selling online monitoring systems for transformers. So I really understand the value of these monitoring systems, and would like to help you to appreciate the value that online monitoring can bring. So we'll go and get started here. I can advance the slide. So for our agenda, we will first start talking about the different fluid types. So this is becoming a bigger and bigger issue as a lot of people are moving away from mineral oil and moving to other fluids. So we'll talk a little bit about those, the fluid types, why measure hydrogen, the transformer gassing phenomenon. So what happens, where does that gas come from when a oil sample or a monitor starts showing that your transformer is gassing? Hydrogen in transformer use cases. So it's important that we understand why hydrogen, again, is important, but then look at some use cases to see real world cases of when hydrogen was used to act on the health of the transformer. We'll look at an accounting model and justification for online monitoring, and then look at the things you probably want to look at. Many of the things you might come up with more, but there's a nice list of things you want to use when you're evaluating online transformer monitors. So for those that aren't very familiar with transformers, we generally put them in three different categories. We have power transformers that are generally the larger transformers. Most people consider power transformers. You got large power transformers that are generally 100 MVA, and you got medium power that's probably around 30 to between 30 and 100 MVA. And then you have distribution transformers that are smaller, and sometimes you call like a 30 MVA a distribution substation transformer. And so those can look like smaller versions of large power transformers. They can be pad mount transformers, pole top transformers. And so there's a variety of different transformers that we call distribution transformers. And then there's instrument transformers. And so instrument transformers are actually measuring voltage and current in a substation. Generally, the lower voltage instrument transformers today are dry type, so there is no fluid inside, but as the voltage increases, it makes it more and more economic to have a fluid-filled instrument transformer. And so usually once you get up to 138 kV and up, you'll generally start seeing the fluid-filled transformers. And historically, again, most of those have had mineral oil in them, but now there's a lot of manufacturers that are starting to put more environmentally friendly fluid in those transformers. So the important thing to note about all these transformers is if they have fluid in them, there's the opportunity to measure gases in that fluid and therefore understand the health of that transformer. And so we'll get into some good use cases here to help understand how that's done. And again, just one more slide, just pointing out instrument transformers. Historically, this has not been a transformer that people have even considered putting online monitoring on. Historically, the online, primarily hydrogen monitors are kind of the size of a small watermelon. And so putting something that large on an instrument transformer just is very difficult from a mechanical standpoint, and there's concerns about the size of the valves and so forth. So today we have very small solid state hydrogen sensors that can even be used on instrument transformers. So I wanted to dedicate a slide just to pointing that fact out. And again, the instrument transformer does need to have some type of insulating fluid inside, either mineral oil or some other ester fluid is typically what you see in these units today. And so just to be a little clear on the various fluids, historically, manufacturers have used mineral oil in anywhere from large power transformers all the way down to distribution and instrument transformers. And still today, that's probably, my guess is probably 95% of what you see out on the field today is going to be filled with mineral oil. A lot of utilities over the last 10, 20 years have looked at other fluids. Silicone oil was popular for a while. It has, I believe, a higher flash point, and so it was popular for certain reasons, but it is not compatible with mineral oil. And so if you have processing equipment that used mineral oil, you had to either clean it very well before you process silicone, or you had to have completely different separate equipment to be able to process silicone. So my understanding is that when you put mineral oil and silicone oil together, there's foaming, and that's a bad thing to get air bubbles in your transformer. So it became, I think there were probably other reasons, but today you still see some silicone transformers around, but not many. Most of the industry is really focused on the ester fluids today. And I call ester a fluid, which is why we're talking about transformer fluid types, because the ester fluids are not considered oil. And so probably the most common natural ester fluid you see in use today is FR3, and that's manufactured by Cargill. You also have Midel, a natural ester, and ABB Biochem. We're working with manufacturers around the world. We've got a company in Japan that's wanting us to evaluate palm oil. And so it's important that if you have these various fluids, there's also synthetic esters like Midel 7131. And there's a lot more today than just these listed, but I just wanted to throw some examples up there of what some natural esters and synthetic esters are. And it is important that when you look at standards, all the standards are really written around, or most of the standards are written around mineral oil. And in some cases, the gassing behavior of these other fluids is very similar to mineral oil. And in some cases, there's some strange things like stray gassing that can happen. Even if there isn't a fault, your fluids can generate gas just if they're introduced to ambient air with oxygen. So these are all various behaviors that you really should look into and work with your manufacturer of those fluids to understand the gassing behaviors of that particular fluid. But in general, many of the sensors in the market work with all these various fluids, but some do not. So if you're using a specific online monitor and you're going to start putting a different fluid in your transformer, you want to make sure that that online monitor is compatible with that fluid, because a lot of monitors out there are not compatible with the ester fluids. And so why is measuring hydrogen important? Well, first of all, the first hydrogen monitor came out around 40 years ago, because when in mineral oil, when you get to temperatures around 150 degrees C in oil, the oil starts breaking down and you start generating gases. And so hydrogen is generated in most fault conditions and pretty much all the significant fault conditions. And as the chart to the right shows, it's temperature on the x-axis and relative magnitude of gas generated for each of the gases listed. So these 5 gases are the primary gases that are used to evaluate the significance of faults in a transformer. And hydrogen, of course, again, starts around 150 degrees C. And as the temperature increases, you generate hydrogen at a faster and faster rate. And so the nice thing about hydrogen is that there are a number of different technologies that measure hydrogen. And so measuring hydrogen in transformers is a well-proven technology and has been, big value to a lot of utilities globally over the last 40 years. But about 20 years ago, multi-gas monitors came out. And so these are, again, the gases that you see when you take a manual oil sample. So most utilities take periodic oil samples typically once a year on their transformers. And so as your temperatures increase, you start seeing methane, ethane, ethylene, and generally once you've had an arcing in the transformer, you get acetylene. And so as you're getting those other hotter gases, you're also generating hydrogen. And so if you're only monitoring for hydrogen, you of course don't see what's going on with those other gases. But typically utilities and people that are are monitoring their transformers, whether a multi-gas monitor goes into alarm or a hydrogen monitor goes into alarm, indicating that you have increased gassing, you do the same thing. You go out and you take a manual oil sample to confirm what's going on with your transformer. And so when your gas levels increase, it means that there is some active fault in the transformer. Something is getting above 150 degrees C, and you need to pay attention to that. And so sometimes that's a temporary fault, sometimes it's a continuous fault, and it may be indicating an imminent failure. So you really want to watch the rate of change of the gassing and the trend of your gassing in your transformer. So we'll look at some of those a little bit later on. So hydrogen is generated in most fault conditions. When hotter gases are produced, hydrogen is produced as well. And a common question that I've gotten over the years is, why do manual samples often show other gases but not hydrogen? And so I had a customer tell me one time, well, I don't have a hydrogen problem. I have methane, or I have ethylene, or I have, whatever. But I never see hydrogen on my samples. And so I asked them, how do you take your oil samples? And there is a proper methodology that's supposed to be used. You're supposed to purge oil before you take the sample to ensure any dead volume of oil or moisture is purged from the valve. And then you take the oil sample in a glass syringe, and it's airtight to make sure that when it gets to the lab, you've got the best possible sample going to be analyzed by the lab. And so this customer told me, well, they opened the valve and put the oil into a container and then use the syringe and suck the oil out of the container. And so hydrogen is not a gas that likes to stay in a transformer. It doesn't like to stay in oil. It is very volatile compared to the other gases and will escape. If your transformer is not tight and you had a gassing event 6 months ago, it's likely that hydrogen will have all escaped by the time you take your oil sample. Or if your transformer is tight and the hydrogen is still present, if you're not taking oil samples well, that could also be a reason that you don't see hydrogen in your oil samples. And so the nice thing about online monitoring is now if you're monitoring gassing continuously, it gives you an idea of what was going on with the transformer, what was going on with the system. Was there a through fault? Was there, did the substation trip out for some reason? Was there some kind of event that caused an overload? If one transformer tripped out and all the load was put onto another transformer that normally doesn't see that kind of loading. So there's a lot of things that happen that generate gassing in transformers. But by having online monitoring, you're able to, first of all, tell when that gassing is happening pretty much in real time. And you're also able to have an idea of the severity of the issue by looking at the trend of the gassing and see, was it a one-time gassing event where a little bit of gas was generated, but there was no permanent damage done? Or if permanent damage was done, you'll see continuous gassing, and that, of course, is when you want to look at taking the transformer out of service. So the prior chart that we just looked at was in the 2008 version of the IEEE C57.104 guide. In 2019, that guide was updated, and this is the new chart. And so this chart is a different way of presenting essentially the same information. And so what you see here is the hydrogen in blue is going down in the middle of the chart. So when people first look at this chart, they say, oh, well, yeah, I don't produce hardly any hydrogen in the middle section when I'm creating my methane, ethane, and ethylene. And so, is hydrogen really important? And so to understand this chart, you have to look at what it's really telling you. So what this chart is telling you, of these 5 gases, of these 5 diagnostic gases, you got to look at the y-axis, says it's the relative percentage of those gases in your oil sample. So when you take an oil sample and when you have lower temperature faults, say in the partial discharge range, when you have partial discharge, you get a lot of hydrogen followed by methane. And so you might see, if you have, one partial discharge event, you might see 10 ppm of hydrogen and 2 ppm of methane, or 100 ppm of hydrogen and 10 or 20 ppm of methane. So that would be classic partial discharge. Then as you move up the chart into the higher temperatures, your methane starts coming up, your ethane starts increasing, and your ethylene starts increasing. And so what this chart is showing is the total magnitude of those other three gases compared to hydrogen. The magnitude of the combination of those gases is greater than the amount of hydrogen that's being produced. And so that's why you see the hydrogen line go down on this graph. It does not mean that hydrogen isn't being generated. It doesn't go down to zero. It just means that you're generating those other gases, the total combination, at a greater rate than what you're generating hydrogen in that range. As those other gases start dropping off, hydrogen continues to increase. And when you get acetylene, you get lots of hydrogen. Okay, so this graph is a little more difficult to understand than the prior graph, but it is still essentially showing the same information, and it is what's in the current 2019 version of C57.104. And so this kind of summarizes this, what I just talked about. Again, in the middle range, the combination of methane, ethane, and ethylene is greater than the amount of hydrogen being generated at that time, but it doesn't mean that hydrogen is not being generated. And so if you're just looking at a hydrogen trend and slowly increasing the temperature, you should see a trend line like what you see up in the top right of this slide. Okay. And this slide also shows the prior graph. And so you can see how fat the methane, ethane, and ethylene are in that middle range, and the magnitude of the amount of hydrogen being produced. So it's very difficult to represent these things easily. And so then as we get to more complex charts, it gets harder to understand. So from my understanding, both these charts are essentially showing the same thing, just in a little bit different ways. Okay, so let's look at the gassing phenomenon. What is going on? Where's this gas coming from? So it's important to note that when we're talking about 150 degrees C in a transformer, we're not talking about the whole transformer getting to 150 degrees C. You definitely would not want to touch a transformer if it was at 150 degrees C. What we're talking about is some point inside the transformer, whether it's a loose connection, somewhere, if it's overheated core, or some point somewhere in the transformer is getting above 150 degrees C. Okay, so what happens when we get above 150 degrees C? Okay, we generate some gas. Okay, and so when you generate that gas and we see a bubble there, what happens to that bubble? Okay, the bubble's going to go up to the top of the transformer. So if there's a gas space in the transformer, which is very popular, these transformers are very popular in distribution globally, mostly in the US. A lot of transformers internationally don't have a headspace, but the principle is still the same. Gas is lighter than oil, so it's going to go up to the top. And typically, if you take an oil sample from the top of a transformer and the bottom of a transformer, your gas levels are going to be higher at the top than they will be at the bottom. Most samples are taken from the bottom, so all the standards and analytics are based typically off oil samples that are taken from bottom of the transformer. But the ratios should still be about the same whether you're looking at the top or the bottom. So if you're in the gas space, and we're talking specifically about hydrogen here, but it should also apply to the other gases. What happens to hydrogen in the gas space? And at H2Scan, we know lots about this because we make hydrogen sensors, and so we calibrate and validate those, and have spent years and years, studying this phenomenon. We know that hydrogen equilibrates very quickly in gas space. Okay, so if you're looking at the gas in the transformer, when gas is generated in the transformer, you're going to see that gassing very quickly in the gas space, because again, the gas is going to go up inside the transformer. And then eventually, once it equilibrates in the gas space, then it ends up equilibrating in the oil. Okay, so how fast it equilibrates in the oil is depending on a number of things. First of all, what type of fluid do you have? what is the temperature, how hot is the winding, how much is the oil or fluid moving around the transformer. And especially if you're monitoring at the lower valve, it's going to take longer to equilibrate there than anywhere else in the transformer because it's typically a lower amount of flow, but it still gets there, and that's where you take your manual samples. So that's where we're used to taking samples from, and that's usually the easiest place to install a monitor. But if you can get to that top valve, whether that top valve is in the gas space or in the fluid, you're going to see results faster if you're monitoring there. And so I've got a good illustration of that coming up in one of our use cases. Okay. So again, you can monitor in the gas space or you can monitor in the oil. It's important to recognize that if you take a gas sample in the gas space, there's about 20 times as much hydrogen as what you measure in the oil. And so if you have a monitor that's monitoring in the gas space, sometimes the monitors will actually do a in-oil equivalent, provide an in-oil equivalent. So essentially divide that gas number by 20 so that whether your sensor is monitoring in the gas space or in oil, it's giving you the oil value that you are used to using. So it's important that there's something called Ostwald coefficients for how that particular gas behaves dissolved in oil. And so it's important that you're using the right coefficients in your calculations and so forth to understand exactly how much to perform that calculation for moving that gas value into an oil value. I created this slide several years ago, and I think one day last year I was looking for some transformer videos on YouTube, and I ended up coming across a video that illustrates this phenomenon very well. And in this video, it actually shows a spark under oil. You see a bubble come up and pop at the top of the oil tank. The top of the transformer is off. So I encourage you to go look at this video to see get a real live understanding of the gassing phenomenon in transformers. Okay, so here we're going to go through an actual multi-gas case. And this is a very large transformer. This is 1100 MVA transformer, generator step-up transformer at a nuclear plant. And in this case, this is about a month-long trend. This scale is a logarithmic scale, so we can see what's going on around 1 ppm as well as what's going on at 1,000 ppm. And what you see here is acetylene. We come along, and all of a sudden, you get some acetylene in the transformer. So acetylene pops in at about a half a part per million, and over a 2-day period gets up to about 4.5 parts per million. Okay. While you look at the other gas trends, your hydrogen, methane, ethane, ethylene, are all increasing at the same time. And so hydrogen specifically goes from about 30 ppm to 277 in 2 days. Okay, so when you get a little bit of acetylene, you get lots of hydrogen. And this illustrates that very well. And so if we look at the analytics for this case, using the multi-gas analysis, oh, I thought I had the analytics in here. Looks like I don't. So the internal inspection ended up showing an overheated crimp connection. And just to tell you what the analytics showed is it showed initially a fault in paper that was migrating to a fault in oil. And so what we see here is this fault was initially in paper because this overheated crimp connection was wrapped in paper, but it ended up burning the paper away. And as oil started getting to the connection, then it started arcing, and it migrated from a fault in paper to a fault in oil, and the analytics on the Duval triangles showed that. Okay. Also, at the end of that was a crimp connection in the middle of a low voltage lead. When they took the paper off at the top of the leads, at the bottom of the low voltage bushing, they saw that a number of the conductors closest to the winding were all overheated. And so what they found out is that there was a design issue with this transformer. By the way, this transformer was only about 2 years old at the time and still under warranty. And so it's important to find out about these problems while it's still under warranty. And it's also nice to have the monitoring that tells you about the problem prior to the transformer failing. And so in this case, the design issue was that They should have taken measures to ensure that these conductors closest to the winding were not overheating, but they did overheat, which caused the overheating in that crimp connection, which is what was indicated by the gassing. And it's important to note, as we go back to the gas trends, if you would have had a hydrogen sensor on this transformer, and only a hydrogen sensor, what you would have seen is a drastic increase in hydrogen very quickly. In this case, what they did was they, again, took a manual oil sample. So they had the multi-gas analyzer. It was telling them there was a problem. They took a manual sample, confirmed it, and the green line in the middle that has a downward trend at the end, that's the load on the nuclear plant. So within about 24 hours after the monitor notifying them that there was a problem, they were taking the nuclear plant offline. So this is the value of having the real-time data. If they would have waited for an annual oil sample, this transformer likely would have completely failed while the nuclear plant was online. That would have been a big issue. Okay. So then I had another use case where a hydrogen monitor triggered an alarm on a 500 MVA generator step-up transformer. And in this case, the analytics showed the triangle 1 showed that there was a fault about 650 degrees C. Triangle 4 showed possible carbonization of paper. Triangle 5 showed that there was a fault in paper near the border of a fault in oil. Okay, very similar to the last case we just looked at. And in this case, again, low voltage connection, which is where there's high current. At the bottom of this low voltage bushing, there was nut had loosened up on a connection, creating a high resistance connection. The customer took 3 manual samples over 2 weeks, and the last one showed a settling, indicating that there was arcing, and scheduled the unit for an outage where they performed an internal inspection, found this, and they were able to save this 500 MVA GSU. But as far as I know, is still in service today, a number of years later, because of the hydrogen monitor alerting them to the problem. And it was important to note that this transformer, again, was only in service 2 to 3 years before this problem was found. And again, the online monitor alerted them. They were able to take an outage and actually save this transformer. And in this case, the plant did not have a spare transformer, so it would have been a huge issue, out of service for a long time while they sourced another transformer and got it to the site and got the new transformer installed. So this is a much more recent case. This is a customer that did a number of hydrogen sensor installations last year. The top picture on the right shows the sensor installed at the top of the transformer. As you can see in the bottom picture of the transformer is a conservator unit, which indicates oil goes all the way up to the top of the tank. So this tank does not have a nitrogen blanket. This is a 33 MVA transformer. This transformer is 27 years old. So usually you expect these types of transformers to last 30 to 60 years. This one's been having problems, which is why they wanted to install the monitor on it. So the interesting thing here, first of all, to explain what happened, there was a down conductor. The conductor literally broke. So there's some pictures of the conductor, the line actually broke. And in this case, it created a through fault on the transformer and some gassing. So when there's a through fault, there's high current when that conductor hits the ground. Something in the transformer overheated for a short period of time, generated some gas. So if you look at the magnitude here, the magnitude was only a couple ppm. So in general, most people aren't concerned about 2 ppm of hydrogen. It's also important to note that the yellow arrow there indicates the timing on this graph is backwards for some reason. We actually got this from the customer, so we're actually using their data here, but this is the way the graph was shown. So what happened, the shaded area was the time during, I'm not sure if it was when the transformer was out of service or the feeder was down before they restored service. But in any case, within about 30 minutes, the conductor going to the ground and the transformer seeing the through fault, on the sensor, again, mounted at the top of the transformer, they saw hydrogen. Okay. What they saw was a few ppm of hydrogen. Then a few hours later, another little bit of hydrogen, but as the hydrogen dissolved in the oil, migrated all around the transformer, and went back down to non-detectable levels. So this is a through fault that could have caused permanent damage to the transformer and caused the transformer to fail. But in this case, the customer was very happy to see that, hey, the sensor's working. It saw some gassing during the through fault, but the through fault did not cause permanent damage because they didn't see continuous gassing coming from the transformer after the through fault. So they felt confident leaving the transformer in service, and no further action was required. Okay, so the next case, this again is very recent information. This transformer, a 24 MVA transformer, 12 years old. So this transformer, I'm not sure if there were design issues. We don't know a lot about the history of this transformer, its operation, but there had been a close-end through fault, we know, right around the time the sensor was installed. They actually had taken the transformer out of service, degassed the oil. They couldn't find any problems and put it back in service. So it shows there April 19th. The transformer was energized after gassing investigation, found no issues. They couldn't find any issues with the transformer. So again, having the sensor on the transformer, all of a sudden at 2 o'clock in the morning on May 8th, hydrogen started increasing very quickly, went up to around 80 ppm. Took them a while to go out and get a sample. Again, this is a utility that doesn't have a history of using online monitoring data. So this really illustrated that there really is value in hydrogen monitoring. So on May 20th, they went out and took an oil sample, and the sensor at the time was reading around 83 to 85 ppm. The manual sample showed about 80 ppm of hydrogen and 52 ppm of acetylene. Of course, when they saw the 52 ppm of acetylene, they scheduled an outage, took the transformer out of service, again, did an internal inspection, and found that actually the lower part of the winding was coming apart. And so this was permanent damage that was done to the transformer. If they would have left it in service, it would have failed in some period of time, likely in the shorter time frame rather than a longer time frame. If they had waited for the next annual oil sample, it's likely this transformer would have failed prior to the next sample. So again, 12-year-old transformer, and there's great technology out there today that allows you to monitor these transformers. Okay, so here's another online monitoring solution at a solar farm. And in this case, the sensor is mounted in the gas space. And this transformer is actually running several thousand ppm of hydrogen, which is why they wanted to install the monitor. So if the trend starts increasing very quickly, they'll be alerted to significant damage of the transformer. So they will, of course, take it out of service. But right now, everything seems to be at equilibrium. They've got a cell modem there, so they're pulling data back regularly to monitor and alert them to an issue. So the issue with a lot of these pad mount transformers is they generally are not in substations. At a solar farm, they may or may not be, but when you're looking at monitoring data from pad mount transformers, wireless options are becoming very popular. So when you look at an accounting model or justification, there are absolutely transformers you need to have multi-gas monitors on. Generator step-up transformers, SIC transformers, transformers that are critical to different processes. You definitely want to have multi-gas monitors on, but the price in general it's very difficult to justify putting those on all of your transformers. And if you look at a transformer fleet, most utilities are looking at around a 1% failure rate. And if you have 1,000 transformers or 5,000 transformers that are, that you need to be monitoring, it's very difficult to justify putting multi-gas on all those. So it's nice to have the data, but with such a low failure rate, you need to look at where you're going to get the most bang for the buck. And so in this case, we just took what might be a typical utility, 6 power plants. You have about 30 critical transformers and 3,000 other transformers that they'd love to have monitoring on, but multi-gas is just too much in the budget. So if they have, let's say they have $3 million a year to spend on multi-gas monitors, And let's say an average cost of a multi-gas monitor installed is 60,000. Today, I understand it's, depending on what you're doing, it's likely going to be more than that. So, but at this, using these estimates, you're looking at about 50 monitors per year. Well, if you have that same fleet of 3,000 transformers, for that same $3 million, you could be adding monitoring to 300 transformers per year. And over a 10-year period, actually get monitoring on every single one of those transformers. And now the value of that is, again, whether you have a multi-gas or a hydrogen monitor, you're going to be taking a manual sample to confirm what the issue is. And once you have that multi-gas analysis from your manual sample, now you're able to determine, can I keep that transformer in service? So generally your action is the same whether you've got a multi-gas or a hydrogen monitor installed. So and most people have a multi-pronged strategy where, again, they on their critical transformers, they're going to install multi-gas and typically other types of monitoring as well. But on a large scale, it's difficult to justify moving that on a large scale. So that's where hydrogen monitoring really comes into play. And so utilities, of course, would rather spend capital dollars than maintenance dollars. At least in the US, there is generally the public utilities, their rates are based, their rate of return, they earn a rate of return on their capital investment and earn a lower rate of return or no rate of return on their maintenance dollars spent each year. So if they're spending capital dollars on these monitors, in general, it's not a big deal to buy the multi-gas because it's capital expenditure that you're earning a rate of return on. But what happens is those can also be expensive to maintain. And so if multi-gas monitors last 5 or 10 years before they need maintenance, and it's going to hit your maintenance budget, then it gets hard to keep those running, and you may or may not be able to replace those on capital depending on various accounting rules. And so again, large expenditures can be capitalized. There's a lot of utilities that have limits. Small expenditures are usually maintenance. And so, but there is an industry trend to make online monitors a unit of property. So regardless of the cost of the monitor, it can be capitalized. And so it's difficult for utilities to rectify the life expectancy. Typically, 20 to 40 years on a transformer, or 30 to 50, depending on your utility, where a typical monitor is going to last 10 to 15 years. So how do you rectify that? How do you keep monitoring your critical assets? And so those are challenges that asset managers have to deal with. And so when you're evaluating transformer monitoring solutions, you want to make sure you do a complete evaluation. So, in today's world, it's really all about the data. What data do you really need to make informed decisions? Okay, do you need different data for different transformers? From your multi-gas data, you're going to get more data, but is that going to actually provide more data than just hydrogen? There are people working today on hydrogen models that will tell you the type of fault in your transformer based on just the hydrogen trend. Are there other important parameters to measure? A lot of people are moving to very reliable systems where they just have a bushing monitor and a hydrogen monitor because they've, depending on who you're getting your multi-gas monitors from, a lot of them require a lot of maintenance, and that, of course, is not preferable. I've heard a lot of customers say that they're tired of maintaining their monitors more than they're maintaining their transformers. And so that becomes a big issue. And, so having good, reliable monitoring is important. Also, how are you going to get the data? Are you going to put an alarm contact into SCADA? Are you going to bring back the real-time data? You're going to aggregate all that data for all your transformers, use AI to do your own analysis. There's a lot of options today, and a lot of utilities actually have people who will manage that data. So if you're not somebody that has somebody that is set up to manage that data, that can be an issue. So you need to understand how you're going to get the data and who's going to be responsible for the data. And if maintenance is required on your monitors, is that covered by a warranty? Is it covered by an extended maintenance program? Who's going to pay for the maintenance and who's going to perform the maintenance? Some monitors, some monitoring vendors don't allow you to perform maintenance on your own monitors. So you're required to use their service folks to come in and maintain the monitor. And is maintenance training required? So some vendors will train the customers to do their own maintenance. And so that's another thing to evaluate. How long is a monitor warranty? And we understand that a lot of people are moving to a 10 manufacturer. You to understand what is the cost for, say, a 10-year warranty. We've heard some customers tell us, oh, the cost of the monitor actually doubles if they're going to provide a 10-year warranty over a standard 1 or 2 year warranty or something like that. So these are things you want to understand because that really gives you an indication into even monitors that aren't designed to have maintenance, what once you stick them in a substation, the real world does to them, what's that really going to cost over 10, 20, 30 years of having that monitor on your transformer. So, of course, what is your monitor life expectancy? Which vendors do you trust for short-term and long-term support? I've worked for some different people, and some vendors have very good reputations in the industry for service, and some aren't so good. So you want to make sure you're working with somebody that you can trust. And when you're looking at, say, hardware and installation and even maintenance, so if most monitors are going to last 10 to 15 years, well, what's it going to take to replace that monitor? Is it a 10-minute change out, or are you looking at a full day or 2-day change out? And what issues is that going to cause, and how are you going to handle that when the time comes? So these are all things that are important to evaluate when you're monitoring or when you're putting together a monitoring solution. So I encourage you to reach out to me if you have any questions or would like more information about monitoring products that H2 Scan supports, or we actually provide sensors to a lot of folks in the industry, and so we can help you understand more about the various types of technologies used and the pros and cons of using them.